In the history of human civilization, no element shaped destiny more than water. It carved valleys, nourished fields, and dictated where empires could rise. Yet some of humanity's most enduring achievements began not beside rivers, but far above them. On dry plateaus, arid hills, and fortress mountaintops where water refused to flow, ancient engineers found a way to make it climb. This is the story of how the ancients learned to defy gravity. Thousands of years ago, the earliest experiments with water movement began in Mesopotamia, the land between the Tigris and Euphrates. The first farmers who settled there understood the river's moods. They dug canals to bring water to their fields, but when floods receded and land rose beyond reach, they turned to invention. The solution came from simple observation: a bucket, a lever, and a counterweight. The shaduf, a long pole pivoted on a frame, became the first device that allowed humans to lift water upward. A single farmer could dip a bucket into a canal and swing it to a field a few feet higher. It was slow, but it worked, and over centuries, thousands of shadufs lifted entire harvests out of the floodplains. But even then, the challenge remained: how to move water not just a few feet higher, but hundreds. The ancient Egyptians took the idea further. Along the Nile, their temples and cities rose far above the riverbanks. They developed a sequence of lifting mechanisms, multiple shadufs in a line, each raising water to the next. By the time of the New Kingdom, they had created irrigation chains capable of feeding entire settlements perched above the floodplain. The Egyptians also experimented with the sakya, or water wheel, a rotating device powered by animals walking in circles. Wooden pots fixed to its rim scooped water from a channel and emptied it into aqueducts running uphill in gradual slopes. Each revolution turned muscle power into hydraulic progress. Though primitive, these early machines established a principle that would echo across continents. With the right geometry and patience, water could climb. Across the desert in Persia, where rivers were scarce and rain unreliable, engineers faced a more difficult problem. The Persian plateau was dotted with towns surrounded by dry hills. To survive, they built one of humanity's most ingenious hydraulic systems, the qanat. A qanat began in the mountains, where snowmelt and groundwater collected deep underground. From there, diggers carved a gently sloping tunnel that could stretch for tens of kilometers, descending so slowly that water moved almost imperceptibly. Vertical shafts provided ventilation and access for workers. At the end of the tunnel, water emerged at a lower elevation, fresh, cool, and reliable. Qanats were not about lifting water, but about controlling its descent. Yet they taught a crucial lesson: gravity could be managed, not just obeyed. The Persians realized that to make water climb, you first had to understand how it flowed. Farther west, in Greece, the principle of pressure began to emerge. The Greeks studied how water sought its own level. They learned that a sealed pipe could carry water from a higher source to a lower point, and then back up again, if the outlet remained below the source's elevation. This discovery became the foundation of the inverted siphon. When the Romans adopted and refined Greek hydraulic science, they took it to monumental scale. Roman aqueducts are often remembered for their graceful arches crossing valleys, but their true genius lay in what could not be seen. The aqueducts maintained a constant, gentle gradient, sometimes only a few centimeters of fall per 100 meters, allowing gravity to do the work. But when valleys grew too deep or terrain too steep for a straight line, Roman engineers created enclosed lead or stone pipes. These pipes descended into the valley and then rose again on the opposite side, driven by hydraulic pressure. Water, confined within the pipe, pushed upward until it reached equilibrium with its source. It could climb hills, feed cities, and even reach fortress citadels perched hundreds of feet above the plains. At the heart of this innovation was mathematics, the understanding that water could be compelled to rise if only the engineer respected its laws. One of the greatest examples was the aqueduct of Lyon in Roman Gaul. It carried water across deep valleys using multiple inverted siphons built from precisely fitted lead pipes. Each section required intense calculation, the thickness of metal, the sealing of joints, and the pressure within bends. A single flaw could burst the line. Yet, through mastery of pressure and gradient, the Romans delivered thousands of gallons of water uphill each day. Their techniques spread across the empire, from Carthage to Tarragona, from Jerusalem to Constantinople. Fountains and baths flourished on heights that, by nature's rule, should have been dry. While Rome was building stone monuments to water, the Indian subcontinent was constructing architecture that embodied it. In western India, where the monsoon determined life and death, engineers built step wells, monumental shafts that descended deep into the earth. Unlike wells meant for drawing water, these were social and architectural marvels. Multi-storied corridors, staircases, and chambers cut into rock. But step wells were also part of a broader system. Water from seasonal rivers was stored in artificial reservoirs, then channeled upward through a series of terrace steps and manually operated lifts. In regions like Rajasthan and Gujarat, camel-driven wheels with clay pots brought water from deep wells up to castle cisterns. At Hampi and other fortified cities, hydraulic systems, combined reservoirs, elevated tanks, and stone conduits that distributed water even to the highest palace courtyards. Archaeologists studying these networks found evidence of primitive valves, pressure chambers, and gravity-fed overflow systems. The ancient Indian engineers, without the mathematics of Rome, achieved equilibrium through observation and design intuition. Water was not forced, it was guided. Meanwhile, in China, hydraulic engineering reached an entirely different scale. By the 3rd century BCE, the Chinese were using chain pumps, rotating loops fitted with paddles or discs, that lifted water continuously from canals to higher fields. The principle was simple, but brilliant. A wooden frame held a moving belt fitted with blades that scooped water upward as it turned. Powered by human or animal strength, the chain pump became the heart of Chinese irrigation for over 1,000 years. Later, with the spread of the water wheel, these pumps became self-operating machines. Through ingenuity, not machinery, civilizations from Egypt to China transformed gravity from a barrier into an ally. By the Middle Ages, the challenge of carrying water uphill had become central to defense. Castles built on high ground for safety needed reliable supplies during sieges. Wells were dug deep into bedrock, sometimes reaching hundreds of feet. In some fortresses, like the Crac des Chevaliers in Syria, cisterns collected rainwater from rooftops, filtered it through sand, and stored it underground. In others, engineers revived ancient techniques, animal-powered wheels, bucket chains, and pressure-fed conduits supplied citadels that seemed unreachable. In Europe, windlasses and counterweight lifts hoisted water manually from deep shafts. In Islamic Spain, the technology of the noria, a large water wheel fitted with jars, lifted river water into elevated aqueducts that fed Al-Andalus's gardens and palaces. The wheel turned endlessly, driven by the current itself, each revolution conquering gravity one step at a time. What connects all these civilizations is not just engineering, but understanding. Each culture, in its own way, studied how nature moved water, and then found the minimal force needed to change its direction. The Mesopotamians discovered leverage. The Persians mastered gradient. The Greeks defined pressure. The Romans refined containment. The Indians balanced architecture with hydraulics. The Chinese mechanized motion. Together they wrote the foundations of hydraulic science, long before the word existed. Modern archaeologists and engineers continue to uncover these systems, often buried or broken, yet astonishingly precise. In the deserts of Iran, qanats still flow today, some over 2,000 years old, carrying water from mountain aquifers to fields without pumps or electricity. In Italy, parts of Roman aqueducts still supply cities. In India, stepwells remain cool and functional through extreme summers. Each discovery deepens our respect for ancient minds that worked with observation and stone instead of silicone and steel. In recent decades, scientists have reconstructed some of these water-lifting devices to understand their efficiency. Replicas of the Roman Archimedean screw, for instance, a spiral tube turned by hand, can lift water several meters high with remarkable consistency. The same principle is used today in certain irrigation systems and even wastewater treatment plants. The Noria and Sakya, recreated using modern materials, reveal how perfectly the ancients balanced torque, weight, and flow. They could move hundreds of liters per hour using only animal power or the motion of a river. Each test confirms the same truth. Ancient technology was not primitive. It was optimized. But beyond the mechanics lies something deeper. The effort to carry water uphill reflects humanity's refusal to accept natural limits. To live in places where nature said no, civilizations responded with imagination and geometry. Every wheel, lever, and pipe was a statement of intent, that life could persist anywhere, even against gravity itself. It is easy to imagine these systems as quaint relics, but they were lifelines. A broken qanat could doom a city. A failed cistern could starve a fortress. Each drop of water that reached a mountaintop garden represented hundreds of hours of labor, measurement, and design. The story of uphill water is, therefore, a story of survival through understanding. From the farmers of Mesopotamia to the builders of Rome, from the desert wells of Persia to the hill forts of India, people learned to measure, calculate, and predict. They transformed the invisible laws of nature into visible works of architecture. In their persistence, we find the origin of modern engineering, the belief that every problem has a solution if we are willing to observe carefully enough. Today, satellites trace the remains of ancient aqueducts from space. Archaeologists map lost channels buried under desert sands. Hydrologists model the flow rates of systems that once powered vanished empires. Each discovery reminds us that what we consider modern, the use of pressure, gravity, and gradient, was mastered long ago, carved in stone by hands that sought to bring life to barren heights. And so, when we look upon a ruined fortress, a broken well, or an arch half buried in earth, we are also looking at equations made visible. Geometry turned to faith. Mathematics turned to survival. Humanity learned early that water always seeks the lowest point. But civilization began when we decided to make it climb.